This will be a note on the early history of atomic theories, just kind of a backgrounder for some of the things that we're going to need to get into and we'll be talking about later on. In order to understand the modern atomic theory, we kind of have to know where it came from, and much of what I'm going to talk about here you already have a background on. Because we talked about it already in grade 9, a little bit in grade 10, touched on it in grade 11 if you had my class. And so we're just going to recap some of that stuff so that you are still familiar with it. The first thing that we need to remember is that early on in the early history of our modern world, before science really got a hold of things, we had the earth, air, wind, and fire, the four-element theory of matter. And this was generally proposed by Greek philosophers like Empedocles, Aristotle later on, who supported this idea because it just kind of made sense to them, and it was more of a philosophical debate kind of thing. About 400 BC, there was one Greek philosopher who said, wait a minute, let's think about this in more realistic terms, rather than just trying to make things up and justify it through thought experiments. He came up with this idea: if you take an apple, let's say, and you cut it in half, then you have two smaller pieces. And if you take one of those smaller pieces and you cut it in half, and you get two smaller pieces. And you cut one of those in half and you get two smaller pieces. And if you keep on going like that, eventually you get to a point where the pieces are so small that you can't cut them in half anymore. And when you get to that point, it's not divisible anymore. Atomos is the word that he used to describe that. And so as a result, you eventually get to the very tiniest piece of matter. Now, it was a thought experiment for Democritus as well. He had no evidence to support it, but it was a kind of a revolutionary way of thinking, to think that matter was made up of these tiny, tiny little bits instead of the four elements: earth, wind, water, and fire. So the problem, though, was that Democritus, rather than being in kind of one of these Ivy League schools, didn't have a whole lot of influence around the people around him. And it was such a revolutionary idea at the time that it really didn't catch on. And people who came along later, like Aristotle, even some of his contemporaries, just kind of ridiculed him because of his, really? Everybody knows that, all matter is made up of earth, wind, water, and fire, and how can you think anything else? And so this idea then kind of held on for about 2,000 years after, and so that kind of brings us into what we call the Dark Ages of history, which were really anything but. There were a lot of things happening, especially by alchemists, kind of the forefathers of modern scientists. These guys really looked at nature and tried to make practical uses of the materials around them. And so in doing their kind of alchemy, they actually invented a lot of very revolutionary technology for them at the time. Glassware kind of came into its own at the time because they needed certain jars and containers to carry out their experiments and that sort of thing. And one of the key things that the alchemists wanted to do was to create valuable metals from base metals, so making gold out of lead, that sort of thing, in order to make their benefactors, the kings and barons and all that kind of thing, who they were working for, to make them rich, right? And in the process make a name for themselves. And so this sort of thing kind of happened all through the 1200s, 1000 AD, up until about the 1600s, 1700s, and it was quite common for kings to visit each other and bring the whole entourage with them, and along with that would come the alchemists, and the alchemists would, of course, be part of this whole entourage and then be able to talk to the guys they were visiting, and so they started to make up symbols for elements and all that kind of stuff, and share information between themselves. They weren't really all that rigorous, for the most part, in terms of the scientific method that we kind of adhere to these days, but it was kind of heading in that direction. So around 1660, Robert Boyle was starting to do some work in this area, and he was working with gases primarily, but he was very rigorous and very methodical in the way he carried out his experiments. And one of the things that he came to realize was that really there aren't just four elements. There's actually a whole bunch of different elements. And he's, along with Joseph Priestley, about 1773, discovered that, Priestley's, still kind of adhering to this four-element model, but yet he discovered oxygen. And also discovered that if you take carbonic acid and put it into water, you get carbon dioxide gas bubbles in there. So he essentially discovered pop. But this four-element idea was still very prevalent in their way of thinking. And so until Lavoisier came along and started dealing with, invented, the first really, triple beam precision balance, came up with the law of conservation of mass, and then in 1790 Joseph Prout came up with the law of definite proportions. This is about when scientists started to realize that maybe Democritus was right after all. And this started the, kind of the beginning of the scientific method. We start to see, okay, we're observing this, why is it happening? All right, so these guys started to explain the behavior of matter rather than just trying to make up this airy-fairy idea of, okay, it's made of this much water, this much wind, and so on and so forth. About 1805, John Dalton, who was an English teacher, took a bunch of these ideas, put them together, and finally came up with his particle theory of matter. And his idea is kind of the foundation, the first part of the modern atomic theory. And we're familiar with his 5 principles of the particle theory. Matter is made up of indivisible atoms. All atoms of an element are identical. Atoms are neither created nor destroyed. Atoms of different elements have different weights and chemical properties, and atoms of different elements combine in simple whole number ratios to form compounds. Having said that, now we need to understand that Dalton just kind of formulated this. He had no real evidence to support it. Well, some kind of evidence that led there, but really no idea of what an atom really looked like. And so he envisioned this kind of a billiard ball effect. All right, so that's kind of where the start of the atomic theory comes from. Later on, scientists started to discover that, well, these tiny bits, these atoms that Dalton was talking about, are actually made up of smaller bits, which have charges. And so the invention of the cathode ray tube kind of developed, allowed for the development of these kinds of ideas, because the behavior of matter now was very much different from what we were able to observe previously. And so Thomson was the first one who described electrons, the negatively charged bits. And he pictured it still with that billiard ball kind of look to it. So there's this positively charged sphere and these little negative bits that are embedded in there. And it made sense for them at the time with what they were looking at. Now, there was as we call the raisin bun model, there was a student of Thomson's, Ernest Rutherford, who had a bit of a disagreement with Thomson. And in order to prove it, Thomson actually just said, okay, fine, prove it. And so Rutherford came up with his famous gold foil experiment and set this up so that he could fire these positively charged alpha particles at this gold foil, which he pounded very, very, very thin, like microns thin, set it up inside a device which had a phosphorescent screen around it. And what he found is that the particle beam then passed right through the gold foil, and most of the alpha particles impinged on the phosphorescent screen right behind the gold foil. There were, however, a few glitches, so he saw a few little bright spots appear once in a while on the screen in other positions. And so his kind of takeaway from all of that was that apparently the gold foil is actually mostly empty space. But there has to be about 3% showed a very dense positive space in the middle. And so this is kind of the first use of radioactivity. So now we have further developments. So we get Rutherford proposed that the name proton be used for this positive charged particle in the middle, and electron being the negatively charged particles that are kind of around that central positive charge. He didn't kind of understand, so he assumed it was just an electron cloud, kind of in a sphere around that. And they didn't really at that time know about neutrons. So what we have with Rutherford's model, though, is that we have this issue which came out of physics later on, that if we have these electrons orbiting this positive center, we have to deal with something called electrostatic attraction. And we have to deal with something called, because the electrons are moving, we have to deal with angular momentum. And so if the electrons are orbiting around the nucleus, then they have to be continuously accelerating. According to physics at that time, if they're continuously accelerating, then they are continuously emitting energy. As a result, eventually the electron would have to collapse down into the nucleus, essentially getting a black hole effect, if you want to look at it that way. So essentially the atom would self-annihilate. That doesn't happen. And so Rutherford's model kind of breaks down there because his theory doesn't support what we're actually observing. All right, so a couple of other scientists that have kind of added to our understanding of modern physics and our understanding of the atom. Around the early 1800s as well, a lot of people were starting to work with light. Joseph Fraunhofer, for example, he studied absorption spectra of light given off by the sun. The spectrum of dark lines against a light background, the results from the absorption of selected frequencies of the electromagnetic radiation by certain atoms and molecules. Kirchhoff and Robert Bunsen invented a spectroscope that allowed for looking at different kinds of light and looking at emission spectra, where you're looking at the bright lines set against the dark background, which is similar to our spectroscopes that we have in class. In analyzing certain elements, so if you take a specific element, let's say hydrogen, put it into a gas tube, and then with electrodes on either end and run an electric current through, then what happens is the gas starts to glow. And what we find is that the elements, when they're excited, the electrons jump to higher energy levels and then come back down and release energy in the form of a photon. And what we found, and Johann Jacob Balmer was one of the first to discover this, is that for hydrogen especially, there are only 4 lines in the visible region that you can see. And one of the things that he found was that their wavelength or color corresponds directly or fits really nicely into the Rydberg equation, which is here. And if you go into physics later on in university, you will study this in depth and understand the math behind it. Bohr took that information and came up with, did some other experiments, came up with evidence that proved that the electrons exist, that the electrons were causing this, and in order to do that, they have to exist at very specific energy levels. And so this is kind of the advent of this whole idea of quantization, that certain things can only have certain values of energy. So what he discovered is that energy of the electron is directly proportional to its distance from the nucleus. When light is absorbed, the electron jumps from a lower energy level to a higher energy level. When light is emitted, it falls from the higher energy levels back down to the lower energy level. Now, the energy of light absorbed or emitted is equal to the difference in the energy levels of the orbits between the electron jumping up and falling back down. That was key. So we have this model now where we have a positive nucleus, and then we have electrons being able to occupy only certain energy levels around that nucleus. The ground state is called the lowest energy level. The excited states are any energy levels above that. So in order to get into the higher energy levels, the electrons have to absorb a certain amount of energy. They can't be less, it can't be more, it has to be that specific amount of energy. And so you have these step-like sequences where electrons can come back down to the ground state by releasing a certain amount of energy, and then another certain amount of energy, and another certain amount of energy, or jumping several steps by kind of combining those energies and releasing them together. So, because elements have different numbers of electrons, each element has a different line spectra, or a fingerprint, if you like. Okay, and so that leads Bohr to describe the atom in the classic sense that we've kind of gone through grade 9, 10, 11 with, where we have our positive nucleus, neutrons and protons are in the nucleus, electrons in specific orbits around that nucleus. All right. Now, the different spectra of light that come off are not just in the visible region, but also in the ultraviolet and infrared regions. And a number of scientists have kind of worked in these, and the different series are kind of attributed to their work with those. So we got the Lyman series, the Balmer series, the Paschen series, bracket, pun. Now, the Balmer series, or that is those energies that electrons give off that correspond to coming down to the second energy level, are the ones that are in the visible region. Okay, and so what we see then are, so the Balmer series is the most famous one, because these are the ones that correspond to what we can actually see with the naked eye. All right, other scientists. Now, Max Planck, about 1900, he was a German physicist who worked with matter and energy, looking at how matter can absorb or emit only discrete quantities of energy. He looked at how the energy of an atom is quantized, not continuous. And so he's the first one who actually coined the term quantum, or for this tiny little packet of energy. And it's related to the amount of energy is equal to the Heisenberg constant times the wavelength of energy. Okay, now when Planck first made this idea, or postulated this idea, it was incredibly radical. Like it was just way beyond what anybody else was thinking. And so, in fact, it was so much so that Planck himself never really felt that comfortable with it. And so it wasn't until other scientists came along and went, I wonder if this idea actually makes sense. So Einstein, he's the first one who concluded that light is also quantized. In other words, you have these tiny little packets of light called photons. And so he used that idea then to explain what we call the photoelectric effect, where when you heat up metal, metal can give off electrons when bombarded with certain amounts of heat. And this, being able to explain the photoelectric effect, then is essentially the idea that won him the Nobel Prize, because again, this was revolutionary. So, because what's happening with the photoelectric effect, when certain frequencies of light impinge on certain kinds of materials, electrons are given off. Think silicon and germanium, solar cells, that sort of thing. And so what happens is that the light happens to be at the frequency which gives the electrons enough energy to actually jump out of the material, or away from the material. Or from the atom, I should say. Okay. De Broglie's model, our present-day model, kind of started with some of de Broglie's work. He worked with primarily hydrogen as a single electron system, and made the idea. Bohr worked with hydrogen, and his ideas worked for hydrogen and then broke down for some of the other elements. De Broglie was the first one that said, wait a minute, okay, so everybody's working with these particle ideas of material, matter, electrons, and light. If light, we've always looked at it as a wave, and after Einstein proposed that, wait a minute, maybe light can behave as a particle. Then de Broglie said, well, what if the reverse is true as well? And he made the hypothesis that an electron can act like a wave and a particle, and that each has a specific quantum of energy. Now, he proved this mathematically, and G.P. Thomson later did it by experiment. Heisenberg came along and said, okay, so if we have this wave-particle duality, then really there's no experimental evidence that an electron has both a definite path or an orbit around this nucleus, as Bohr previously thought. And so at this point, we're still looking at our positive nucleus and then this cloud of electrons around the nucleus. Bohr thought there was a definite path for these electrons, but there was no evidence to support that theory. Heisenberg came along and said, well, maybe it's the situation where, because we are observing something so small, that the simple act of observing it is actually changing it. And so what we find is that we can't know the exact momentum and position of the electron at the same time. Now, the analogy that I like to use is if you have let's say we go down to the gymnasium and somebody puts a basketball somewhere in the middle of the gym, and we turn all the lights out so you can't see a darn thing, and you fire these baseballs out the middle of the gym, and then all of a sudden you hit the basketball. What's going to happen to the basketball? It's going to start to roll away. So now the simple, there's the basketball. Well, was the basketball. But now we can't see the basketball because it's moved away. And so the simple act of observing the basketball has changed its position. Same sort of thing happens with electrons. The simple act of observing them, we've given them enough energy to actually change their momentum. So we knew where they were, but not where they've gone. Or we can know where they are, but we don't know in what pattern they're moving, right? That sort of thing is kind of what's happening here. So we use the term orbital, not orbit, to describe this region of space where electrons may be found. And this is Heisenberg's uncertainty principle. We can know both we can know momentum, or we can know position, but we can't know both of them. All right. Now, Schrodinger's wave equations we can use to manipulate the three-dimensional orientations of these things and probabilities, and map out a three-dimensional picture of what these orbits will look like. Schrodinger was the one who made the hypothesis that an electron can act like a wave and a particle, and that each has a specific quantum of energy. This, combined with de Broglie's idea of matter waves, with Einstein's idea of photons, he proposed our new atomic theory, which we call the quantum mechanical model. And this is still the one that's kind of prevalent to us today. Now, the quantum mechanical model is steeped in mathematical equations. You really have to understand the math, which means you need to understand some calculus, because it's all based on calculus. Now, Schrodinger developed a model of the atom that accounted for both the wave and particle behavior, and instead of restricting electrons to limited orbitals, circular orbits, he developed this idea of orbitals. Orbitals are regions in space where electrons are most likely to be found. So this idea now doesn't violate Heisenberg's uncertainty principle. The Bohr model does, and so we're kind of moving ourselves away from Bohr's model. It has its uses for explaining kind of elementary principles, but Bohr's model kind of really falls apart when we start looking at this, when we start applying Heisenberg's uncertainty principle. Schrodinger's three-dimensional model now requires three coordinates, or quantum numbers, which describe orbitals where electrons can be found. Now, I'm going to turn you loose at this point to look at some of these elementary histories, looking at the development. The textbook does a nice job of laying this out, so you can have a look, page 168 and 173, to answer those questions to help you in that understanding.